So, let's talk about something that's literally all around us, powering so many of the AI tools we use every single day, language models. We're going to dive into the amazing story of how we taught machines to understand and, well, to speak our language. It really all boils down to this one big question. Every time your phone suggests the next word in a text or your search engine seems to read your mind, there's a language model working its magic. But how? How does it actually do it?
Well, at its very core, it's actually a bit simpler than you might think. A language model is, for all intents and purposes, a prediction machine. Its one job, its entire reason for being, is to look at a string of words and make the best possible guess about what word comes next. To really get what's happening today with this incredible AI, we've got to look back. We're going to take a journey from the very first kind of simple attempts all the way to the breakthroughs that changed everything. We'll even peek under the hood to see how they learn, and then look ahead to what's next. All right, so let's really dig into this, starting at square one. The entire massive field of language modeling is built on this one single, really powerful idea, just predicting what comes next.
This right here is the question that drives every single language model, from the most basic ones to the giants we have today. So for example, if a model sees the phrase, "the sun rises in the blank," it's going to assign a super high probability, like 99.9% to the word east. It just knows that words like car or purple have basically a 0% chance of being right. That's the whole game.
So where did this all begin? How did we first try to crack this prediction puzzle? Well, the earliest major approach was a statistical method called n-grams, and it was a surprisingly simple and honestly a pretty logical place to start.
Think of it like this. An n-gram model has a super short memory. It only looks at a small, fixed window of words right before the blank it's trying to fill. A bigram just looks at the one word before. A trigram looks at the two words before. It's fast, it's simple, but as you can probably guess, it has a massive blind spot.
Okay, to see where this whole idea starts to fall apart, let's look at a sentence. We've got a cat, we've got a bird, and there's this big descriptive chunk right in the middle. The most important pieces of information here are cat and bird.
And this is the kicker, right? If our model is a trigram, it only sees the words all morning, finally. It has completely, totally forgotten about the cat. And crucially, it's forgotten about the bird. It has absolutely no clue what the subject of the sentence is or what it was doing.
And there it is, the fatal flaw. N-grams are trapped by that tiny context window. They just can't see the connections between words that are far apart, and those connections are what give language all its meaning. This was a dead end. We needed a whole new approach.
So, if short-term memory was the problem, what was the solution? Well, it came from a totally new way of thinking about computing, neural networks. This was the first giant leap towards models that could actually start to, remember.
And this journey, it didn't happen overnight. Just look at this timeline. After n-grams in the 90s, the 2000s were all about something called recurrent neural networks, or RNNs. They were a huge step up. But then, 2017 happened, and that changed everything.
The huge leap forward with RNNs was that they tried to read kind of like we do, one word at a time in order. As it processed each word, it would update this sort of internal memory, called a hidden state, trying to carry information from the past along with it.
But it wasn't a perfect system. That memory, think of it like a whisper in a long hallway. The further you get from the start, the fainter it becomes. Important context from the beginning of a sentence could just fade away by the end. Plus, reading word by word was agonizingly slow, which made training these things a real nightmare.
And that brings us to the real game changer, the moment everything shifted. In 2017, a paper introduced a new architecture that didn't just improve on the old way, it threw it out the window. This was the transformer.
And this slide, right here, this shows you the single biggest difference. It's huge. Instead of plodding along word by word, the transformer looks at every single word in the sentence at the exact same time. It sees the whole picture at once. This parallel processing was an absolute breakthrough for speed and scale.
So you're probably asking, how on earth can it read everything at once and still make sense of it? Well, the answer is this incredible, almost magical mechanism called self-attention. It's the transformer's superpower. For any given word, it can instantly look at all the other words and decide which ones are most important for understanding its meaning in that specific context.
Okay, let's go back to our cat and bird. The transformer sees the whole sentence in a single glance. When it's looking at the word finally, its self-attention mechanism creates a super strong connection back to cat and bird. It understands the relationship no matter how many words are between them, and it correctly predicts something like pounced. Boom. The memory problem solved.
Okay, so we have this amazing piece of technology. But how does it get so smart in the first place? Where does all that knowledge come from? Well, it all comes down to a process of training it on just unbelievable amounts of text data, basically scraped from the internet.
You can really boil down this super complex process to a simple little loop. It's like trial and error on a massive scale. The model gets a sentence with a word missing. It makes a guess. Then it compares its guess to the real answer. If it's wrong, it tweaks its internal wiring just a tiny bit to be better next time. Now just try to imagine that loop repeating billions, even trillions of times.
So this technology is obviously incredibly powerful, and it's moving at a wild pace. But with great power, well, you know the rest. It comes with a whole new set of challenges and really interesting problems we all need to think about.
I mean, for starters, just building these things is a huge undertaking. They are trained on data from the internet, so they can unfortunately learn all the biases that exist out there. Then there's the very real risk of them being used to create misinformation. We also have to think about privacy and the sheer environmental cost of the massive computers needed to train them. These are not small problems.
So, what's on the horizon? What's the next chapter in this story? Well, a huge push is to make these models more efficient. Smaller, faster, cheaper. There's a ton of work going into improving their reasoning and making sure they're factually accurate. And the next really big frontier is multimodality. Models that don't just understand text, but images, audio, and video all together. And maybe, most importantly, aligning them with what we as humans actually value.
You know, the story of language models is really just getting started. We've built these incredible machines that can speak our language with stunning fluency. And that leaves all of us with a really big, really important question that goes way beyond the technology itself. Now that they can speak, what do we, as a society, actually want them to say?